Let's start with the first topic. What is sparsity? This is the table of contents of this section. First, we will define redundant dictionary for sparse representations. Then, we will consider underdetermined systems of linear equation. We will also define the L0 norm to mathematically describe the problem of sparse representation. To solve the sparse representation problem, or L0 optimization problem, we here introduce the method of exhaustive search, which is a brute force algorithm and very heavy computation. Now, let's start with redundant dictionary. Let us consider the standard basis for R3. The standard basis is given by E1, E2, and E3 defined here. Then, any vector y in R3 can be represented as a linear combination of these three vectors as this. This is very simple. And not only the standard basis, any three linear independent vectors phi1, phi2, and phi3 in R3 form a basis for R3. That is, any vector y in R3 can be represented as a linear combination of three vectors of phi1, phi2, and phi3 like this. Since phi1, phi2, and phi3 are linearly independent, the coefficients beta 1, beta 2, and beta 3 are uniquely determined. Now, let us consider another set of linear independent vectors of phi 1, phi 2, and phi 3 defined by these equations. Namely, phi 1 is defined by E1 plus E2, phi 2 is E2 plus E3, and phi 3 is given by E3 plus E1. Let us define a set of 6 vectors of E1, E2, E3, and phi 1, phi 2, phi 3, which is a redundant basis for R3, since the number of vectors, 6, is greater than the dimension 3. Then, for a given vector y in R3, we want a signal representation using the vectors in the redundant set, called the redundant dictionary. Since the dictionary, the set of vectors, is redundant, there are infinitely many solutions for the coefficients alpha I and beta I. For example, we have one solution of y1, y2, y3, and 0, 0, 0, but this is also a solution to represent y. Let us take a vector y is 1, 1, 1, which is on the plane spanned by E1 and phi 2 here. Then a coefficient set is obtained as this. This is a sparse representation of y is 1, 1, 1, since it contains many zeros here and here. Now, I will explain why a redundant dictionary is important for sparse representation. Suppose that you have a very small English dictionary with only 1,000 words on it. You need to explain this picture using only words on your small dictionary, which does not have the word elephant. Then you need to try to explain this picture by using many words like this picture shows a big animal that has a long nose, many of them live in African savanna, and so on. However, if you have a very big dictionary with millions of words, you just say, this picture shows an elephant. That is, if you have a bigger dictionary, you can say something with less words. This is why a redundant dictionary is important for sparse representation. Let us generalize the problem of sparse representation with a redundant dictionary. Suppose that we are given a set of vectors phi1, phi2, and phi-n in m-dimensional vector space. If the dimension m is less than the number of vectors n, and m vectors in this set are linearly independent, then this is called a redundant dictionary. The elements phi1, phi2, and phi-n in the dictionary is called atoms. Note that we don't say words for the elements of a dictionary. This is strange, but actually we don't say words for these. For a vector y in Rm, we find coefficients alpha 1, alpha 2, and alpha n such that y is represented by a linear combination of these atoms. We can say that if the dictionary is more redundant, then we may obtain a sparser coefficient set. Now define a matrix phi and a vector x as these. Then the relation of this is compactly rewritten as y equals phi x. The matrix phi is called a dictionary matrix or measurement matrix. Finally, we describe the problem of sparse representation. Given a vector y in Rm and a dictionary matrix phi, which is m times n with m less than n, that is, the matrix phi is a fat matrix, then find the simplest, that is, sparsest representation of vector y that satisfies y equals phi x. This problem is also known as compressed sensing, where phi models an oversampling sensor. Next, let us consider underdetermined systems. Let us consider linear equations with unknowns x1, x2, and x3 given by these equations. Since the number of equations is less than the number of unknowns, there are infinitely many solutions. Actually, all solutions are described by this with real parameter t. Such system of equations is called an underdetermined system. The problem here is how can we specify one unique vector among these solutions? Now, let us consider a detective like Edogawa Conan, an animation character who I believe you know. He solves this problem. The two proofs, that is, equations, are insufficient, and he should seek one more independent proof. If he gets one more proof saying that the criminal is the smallest one among the suspects, to try this, let us consider the L2 norm. The L2 norm of X is computed by using the parameter representation with T, like this. Then the L2 norm is minimized by using T is 1. Therefore, we obtain the unique solution x1, x2, x3 is 1, 1, 1. This is called the minimum solution. Let us generalize the idea. Let us consider linear equations in a matrix form. Phi x is y. The matrix phi is an m times n matrix where m is less than n. That is, phi is a fat matrix. Assume that phi has full row rank, that is, rank phi is m. Then, for any vector y in Rm, there exists at least one solution x that satisfies phi x is y. In fact, there are infinitely many solutions for the equation phi x is y. Here, we formulate the problem of sparse representation by using L0 norm. This is the definition of norms in Rn. A norm in Rn should satisfy these three properties. In particular, the L2 norm or Euclidean norm is defined by this. Also, the L1 norm is defined by the sum of absolute values of the elements. The L infinity norm or maximum norm is defined by the maximum of the absolute values of the elements. This picture shows contour curves of the norm is 1 for L1, L2, and L infinity norms. The L infinity contour is a square like this, and the L2 contour is a circle. The shape of the L1 norm is very important for sparse representation. I will explain this in more detail later. Now we define the L0 norm. Consider a vector x in Rn. The L0 norm of x is defined by this, where SUPP is the support of x, namely, support x is the set of indices I such that xi is non-zero. And this denotes the number of elements, not an absolute value. In other words, the L0 norm counts the number of non-zero elements in X. Note that the L0 norm does not satisfy the first property in the definition of the norm, that is, the L0 norm of 2x is not equal to 2 times the L0 norm of x. Hence, this is sometimes called the L0 pseudo-norm. Now, the problem of sparse representation is formulated as follows. Given a vector y in Rm and a full row rank matrix phi of size m times n with m less than n, find the optimizer x asterisk of the optimization problem given by this. This problem is called the L0 optimization. Here we show a naive algorithm called the exhaustive search for the L0 optimization. The problem of L0 optimization is given by this. For this, we try an exhaustive search. Let us consider the simple example of finding the minimum L0 norm solution that satisfies these equations. First, try the zero vector. This is obviously not a solution. Second, try vectors of x1, 0, 0, 0, x2, 0, and 0, 0, x3. If x1, 0, 0 is a solution, then from the above equations, x1 is 3 and xy is 0 at the same time. This is not a solution. If 0, x2, 0 is a solution, then we obtain x2 is 3. This is a solution. If 0, 0, x3 is a solution, then x3 is 3 and the x3 is 0 at the same time, so this is not a solution. The solution to the L0 optimization is 0, 3, 0. This is the exhaustive search algorithm. Let us consider the exhaustive search algorithm for a general problem. First, check if y is 0 or not. If y is 0, then the optimal solution is 0 vector. Quit. Otherwise, proceed to the next step. Step 2. Find a vector x with the L0 norm is 1. We call this a one-sparse vector that satisfies the equation y equals phi x. That is, set x1 is x1, 0, and 0. x2 is 0, x2, 0, and 0. And xn, 0, 0, 0, xn. And such scalar xi that satisfies y equals phi xi is equal to xi times phi I. If a solution exists for some I, output x asterisk is xi as a solution and quit. Otherwise, proceed to the next step. Step 3. Find a vector x with L0 norm is 2 or 2 sparse vectors that satisfies the equation y equals phi x. That is, we set these vectors and search two elements xi and xj that satisfy y equals phi xij is equal to xi times phi I plus xj times phi-j. If a solution exists for some I and j, then output x asterisk is xij and quit. Otherwise, proceed to the next step. Step K, do similar procedures for k sparse vectors for k is 3, 4, and m. Now, let us consider the exhaustive search is useful or not. As we have seen, it is easily implemented. However, the computation time to find a solution grows exponentially with problem size m. For example, suppose m is 100. Then it roughly takes 2 to the power of 100, which is approximately 1.3 times 10 to the power of 30 iterations at the worst case. If we can do one iteration in 10 to the minus 15 seconds by a supercomputer, then we obtain the solution after 1.3 times 10 to the power of 15 seconds, or 30 million years. This is impossible. The study of sparse representation is to solve such a big and difficult problem in a reasonable time. Now let's conclude this section. Sparsity of a vector is measured by its L0 norm. In sparse representation, a redundant dictionary of vectors is used. In sparse representation, the smallest number of vectors are automatically chosen from a redundant dictionary that represent a given vector. This is called L0 optimization. The exhaustive search to solve L0 optimization requires computational time that exponentially increases as the problem size increases.